So I'm going to go ahead and we're getting started here. Now, if you guys have any questions, make sure you stop me. So pick up, let's see, we've covered bending stress, you know, but last week we did the eccentric loads. So let's just start there, and then we're going to get into this last piece, which is more circle. Okay. I would suggest when we get into more circle that you use a straight edge and a scale and a protract or a compass if you got it, because to draw these things out, you kind of need all of that. You don't have to do this. The math is actually pretty easy, but the graphic aspect of it is what's so cool because it solves things for you that way. So let's let me go ahead and get started here. I'm going to do the slides. We're going to do from this current slide. So I'm just going to review real quick. So last week we talked about combined stresses due to eccentric loads. So I wanted you to work those homeworks in that section. And I don't know if you had a chance to do that much, but basically when we have an eccentric load, what you've got is a load that's off center. So it's producing a moment. So one that has your axial load, instead of right in the centroid, it's off to one side of that. You get this guy called an eccentric load, and that will then subject your member to not only axial stress, but also bending stress due to that moment. Now, those can be very complex because you can have an eccentricity in two directions, which means you're actually getting two moments. And there's a problem or two in the book that deals with that directly. So that's definitely one of the things that we'll look at on Thursday for sure. So, but your bending stress develops from that moment on the applied load. And so you're taking basically that load multiplied by your eccentric distance. So this is a good example of that. If you have your normal load, this would be coming right through the centroid. So there is no moment induced here. So this aspect right here would be zero. But when you have an eccentric load, what you really have is a normal stress developing due to the load itself. And then you have a moment that's being developed here, which is due to the E eccentricity. So if it's off to the side truly like that, you can notice how this bending moment is occurring. It would be putting that in a compressive stress on that front side and a tensile stress on the back side. And if this was further located, not only just straight along the axis, but if it was like, say, one corner of that thing, then you could get a moment coming at you also. So this is what we call an eccentric load. Basically, you're using a process called superposition, where to calculate that, you take and calculate the normal stress, and then you calculate the bending stress, and you add them together. So that's what you're getting. So basically, you get this normal stress, which is just a very simple force divided by cross-sectional area. That's your normal stress. And then you're getting that moment, which is induced, that bending is your force times your eccentricity. And again, the biggest piece you have to look at is which way you think that moment is occurring. Because if it's left of your centroid, it's going to be one type of moment, and if it's right, it's going to be another. So it could be either a compressive on one side, tension on the other, or vice versa, depending on that. But what you essentially then do, you get your bending moment from your MC over I, and substituting the PE in for M, you get PEC over I, right? Like we've developed in chapter 12. So what we have there is we went through those examples. We did this last week. So does anybody need to see a problem or two worked out on this right now? Or you guys feel you're pretty good with
that? Can we maybe just do one as review?
Sure. Do you have a one in particular you want to look at? Let me pull something out, thanks. Did you have anything you wanted to look at for particularly?
No, not really.
Let me see. I did might have, let's see if I got something here I can solve. I'm not sure if I solved this, but I'm going to go ahead and solve this one that I've got because it's a pretty nice one. Okay, and then we can take a look at it and see. Give me a sec. We're going to draw this up and run through this. I think this is a good thing to look at because, you know, I don't know. We didn't get a chance to actually do this since we didn't meet last Thursday, but we'll have plenty of time today or this week to finish that up. So, okay, so we're going to have a load. I might have done this. Yeah, I might have done this with you. Let me see if I can find another one because I think I'm trying to get one that I haven't done with you guys. See if there's one out of the book we might want to do. Yeah, here's one out of the book. We'll do that one. Sorry about that. Okay, so we have a load. We're looking at a column. I'm going to do it in two. I'm going to draw this in two directions, but we're looking at a column. And then we're looking down on top of this column. So this is a top view. This is a side view over here. And we have, let me put a centroid. This would be the line of the centroid essentially coming down through like this. But we have a force that's coming down over here. Okay, so it's off centered. It's definitely what you would call eccentric. So it's loaded right here. And this is 15 kilonewtons. And this distance here of eccentricity is 100 millimeters. Yes, so we've got a unit issue we're going to be dealing with as well. So if we look down top, on the top, let me put the centroid locations in here. And stop me if I'm going too fast. Just let me get the problem set up first. So because this thing is bending like this, this would be my neutral axis here. Okay. So this is going to be the neutral axis line. This one right here, that's my neutral axis. And it is, I've got this thing out of whack, the picture's out of whack, but it's 600 millimeters from this side to this side, and it's 300 millimeters this way. Okay, so from top, front to back. Okay, so I take that back. I think I've got this drawn wrong. Okay, no, that's just good. We'll just, let me see this picture. Oh yeah, let me reverse that. Let me change something a minute. Sorry about that. I'm going to draw it more like what it is. Okay, so we're going to call this piece of it looking this direction. Looking this direction is going to be the front of this thing. This column. That's your front. So let me reverse that picture. So this is going to be like this. So I had it 90 degrees. So this is going to be my neutral axis. And this would be the other axis. Okay. So that's my neutral axis line there. So it's 600 millimeters from here to here, and it's going to be 300. So this is drawn more correctly. So this right here is your front. This right here is your back. So this is the front right here. That's your back. Okay, so that's your back, and that's your front. So that force is acting like right about here, coming straight down. So we have a bending moment that's occurring like this. So it's compressing the front and it's tensioning the back. Does everybody see that now? I'm drawing that a little bit more correctly. You guys okay with that? So this would be 600 millimeters across this direction, okay? So we have a normal force that's acting on here, and we have a bending force. So what I probably want to do is convert everything to millimeter or meters, okay? So how do we calculate a normal stress? What's the equation for normal stress? Who can tell me? Max, since you asked it, I'm going to ask you. Can you tell me what normal stress is defined as?
Isn't it shit, a strain over or no, it's something over strain, I believe.
Well, I mean, you could go that direction, but we're looking at just straight normal stress. It's a force and something else. What would this be called right up here? That times that.
Force divided by area.
Force divided by area, right? Force divided by area. So normal stress is just simply force divided by area. So in this case, because this force is just coming down, we're assuming we're not looking at it being eccentric. So the force is just 16 kilonewtons. The area would be 0.3 times the 0.6. So I'm converting 600 millimeters and 300 millimeters into meters, okay? So that would give us the normal force, and that would be a compressive force, right? Because it's coming down. So it would be a compression. So let's see what we come up with there. Did you guys get a number?
83.33.
Okay. You know what the unit would be?
Kilonewtons or no,
You're right. Kilonewton something, right?
Millimeter over millimeters.
Meters squared. Because I converted that. Okay. What is a kilonewton meter? Or a newton meter squared? Another common unit, it's Pascal, okay? So that's a Pascal. So is this stress compressive stress or tensile stress? What's happening to the force here? It's doing what to the column?
Stretching it.
It is? I think it's pushing down on it, right? Pushing down.
Oh, I see. Yeah, got it.
Compression, so we're going to consider that as a negative stress, okay? Compressive, all right? Does that make sense?
Yeah.
Okay, so now we have a moment going on here, right?
Mm-hmm.
So the moment is equal to P times E. So P is 15 kilonewtons. What is E? That's the distance you're offset from the neutral axis, right?
Right.
So that's 100 millimeters. So that would be what, 0.1? Is that correct? Meters, converting it to meters, right?
Right.
0.1 times 15 gives us what?
1.5.
1.5 kilonewton meters squared, right? Which we could also call pascals. Now, This guy's going to tend to be positive and negative because in the back, he's pulling up. In the front, he's tensioning or compressing. Okay.
Okay.
So we can do a little chart here, and we can say top or front rather, and back. So we have a normal stress, and we have a bending stress. We haven't calculated. I need to back up. I screwed up here a minute. I went ahead of myself. Let me do something. This unit's incorrect. Did nobody caught that? What I calculated was the moment. I didn't calculate the stress yet. How do we calculate bending stress? I got just a bit ahead of myself. Let me erase this stuff. What I said was correct, but my number isn't a stress. What is that number that I just calculated? What's the unit on this moment? Force times what?
Distance.
Yeah, so this would be kilonewton meters, okay?
Okay.
All right, so it's not wrong what I said. It's just wrong what I was using. I was assuming or saying that was the moment or the bending. It's not the bending stress. Bending stress is defined as what? MC over I, okay? So what we just calculated here was M. So C is the distance from the neutral axis to the outside edge fiber. So that would be 300 millimeters or 0.3. And I we have to calculate, right? That would be 1/12 the base times the height cubed. Okay, so let me go ahead and put I here, and then we'll do this properly. Okay, so 1/12 the base is 0.3 times the height, which is 0.6 cubed, divided by 12. Okay, let's see what we come up with here. Okay. I got a pretty small number. You guys check me, okay? 0.0054 meters to the fourth. Do you guys agree with that?
Yeah.
Okay. So using this equation here, I'm going to put the bending equation up here so we got room to do that chart. So my bending moment, my bending stress is going to be equal to 1.5 times C. C is the distance from here to the outside fiber. So that's going to be half of 0.6. So that's going to be 0.3 divided by I. And this will be the right number now, okay? All right, so let's see what we come up with now. I think I blew it already. You guys verify this. Anybody getting that?
No.
Let me check. No, that isn't what I got either. Let me see what I did. Yeah, I don't get that. Anybody get a different number?
I got 83.33.
All right, I just got that too, Max. So I'm going to do it one more time. Make sure. We'll just make sure before we go on. I'm pretty sure that's right though. 83.33. Unit should be kilonewton meter squared. Okay, just check it one more time. Yeah, I get that, 83.33. Okay, everybody else okay with that?
Yep.
Okay, so now this one will have plus or minusness to it because remember in the front, it's compressing, so it's a compressive stress in the front. In the back, it's a tensile stress because it's pulling here and pushing here, okay, due to that eccentricity. So what we do now is can calculate, I'm going to get rid of this guy here. We can now calculate the combined stress due to both loads. So again, we have the front situation and we have the back situation. So this is front and this is back. So we have a normal stress. Normal stress front and back is compressive. So that's going to be a negative 83.33 for both the front and the back because the entire column is under compression. So if this guy was over here right on the neutral axis, this guy right here disappears. There is no moment. But since we do have that bending going on, in the front, we have it bending down its compression. So this bending stress here is going to act in compression. So that's going to be a negative 83.33. But in the back, it's going to act like tension. So it's going to be a positive 83.33. So the combined stress due to superposition is just the sum of those. So we take the negative plus that other negative. So we get 166.67 minus kilonewton meters, which we could call that also kilopascals. So what we're saying is this guy's in compression or a compressive stress. So a compressive stress is developed in the front. Is everybody okay with that then? And
Yeah.
what's interesting, what's happening in the back is when we add those two, we get 0. So in other words, there's no stress developing because essentially the bending stress is counteracting the compressive stress. So they just cancel out. Okay. So what happens is we're going from 0 at this end up to 83.33. So if you're doing a pressure diagram like we've looked at before, you would just have a straight linear line going from 0 to 83. So as you step across this, it just becomes more compressive as you get to here. So everything, this whole thing is experiencing compressive stress. Does that make sense now? Even with all my goofy mistakes at first. That's good that you see mistakes like that. I just jumped the gun. I had this written up here correctly, but then I took and called my moment a stress, and it's not. Okay. Is everybody okay with that? That was a good. I'm glad you asked that. So those are problems out of chapter 13 that if you haven't looked at yet, well, I suggest you look at everything out of 13 at this point, okay? So that we can answer some questions specific to that when we get into class on Thursday, okay? Any other question you want to take a look at before we move on?
No.
Did that
No,
help?
we're good.
Did
Yeah.
that help? Okay. Now, sometimes you're going to look at some of those are Mike beam problems. So what happens is this rotates, this situation kind of rotates 90 degrees. And so then you actually have two bending moments going on. So you have a bending moment due to the load, but you also have a bending moment due to like pre-stressed cables within it, okay?
All right.
So instead of a single bending moment, you're going to have two, okay? And there's another problem in the book, which is kind of interesting. Instead of the force coming down right along one of the axes, it's actually shifted in two directions. And they're going to have you calculate the four corners to determine stress, because the stress will be different on all four corners. So we'll look at that one probably, well, definitely we'll look at that one in class. But it's not hard, it's just you have to think about what's going on from the two directions. Okay, so it's kind of, we're looking at like more of a one-dimensional thing, where that one's more three-dimensional. Okay, no problems? Can we move on?
Yep.
Okay, so let's go back. I'm going to go ahead and clear this because we're going to come back here anyway. Let me jump back in. Okay, so what we're going to take a look at today is dealing with what we call combined normal and shear stresses along a plane. So this can get really, really involved. In fact, there's quite a few pieces in the chapter leading up to this, but we're going to jump into something called Moore's circle, which is just an easy way of solving this kind of process. Now, it seems a bit hard at first, but it's actually really probably one of the easiest things you do once you understand it. But what we're looking at is combining stresses that arise due to the combination of normal stresses and shear stresses. So what we were just looking at was combined stresses of normal stress and bending stress, but we've kind of ignored shear. So now what we're looking at is what happens when you combine the other two stresses. So normal stress is that stress that acts normal to an element, which means it's perpendicular to the cross-sectional area, just like we were looking at before. Basically, it's that force divided by cross-sectional area kind of stuff. And those normal stresses are going to either develop a tension or a compression, okay, which we just looked at. And we typically define tension as positive and compression as negative. And remember, you can do it any way you want as long as you're consistent. But throughout the book, we're pretty much saying tension is positive, compression negative. But shear stress, remember, is going to act parallel to your plane, or in this case, we're going to talk about this little element. So it's just like you just got to visualize it's a very small, infinitely small piece of element that you're looking at. And it develops normal stresses and shear stresses on it. So the shear stress is the stress that tries to counteract the shear force, which is trying to rip that element apart, okay? And what you're kind of looking at is this diagram here. We're looking at, this represents just an infinitely small piece of element of your whatever your member is. And you can notice what's going on here. You have this face, which would be a Y face, and this face, which is a Y face of your element. And this is a normal stress coming in this way or developing. And in this case, it's in compression. And we have an X face over here and an X face over here. And this is also a normal stress. And in this case, I've indicated tension. Now you could have compression in both directions. You could have tension in both directions, or you could have tension in one direction and nothing going on in the other direction. So it just depends on what's going on. But what they're indicating here are what we call shear stresses, and shear stress is developing along this. So this stress right here is referred to as the shear along the X face in the Y direction. So this would be the shear along the X face in the Y direction. And this would be the shear along the Y face in the X direction. So this is the shear along the X face in the Y direction. This is the shear along the Y face, or let me say that again. This is the shear along the X face in the Y direction. And going this way is the shear along the Y face in the X direction. So they basically are kind of rotating or tending to want to rotate this element. Notice this one's trying to rotate it clockwise and this one counterclockwise. So the shear stress will actually have the same value. So if this is 400 PSI, it'd be 400 PSI both, but they're going to have different directions of turn. And so normally you're going to assign a sign there for that. So usually some people use clockwise as positive, counter negative, and vice versa. In your book, Tom uses counterclockwise as positive and clockwise as negative. So he would consider this shear force here, this shear force along the y face would be positive because it's tending to turn it, counter, and this one would be negative. So we just kind of have to keep that in mind as we do these problems. So you get a combination of those where you get a combination of the normal and the shear stresses. They're going to tend to then create stress along various planes within that element. And the big thing you're looking at is what is going to be the combined stress along that plane, or actually the normal stress and the other stress. And then you can determine what that plane is, because those stresses that develop on other planes may be higher than they would be on just the elements plane itself, the X or the Y planes. And so therefore that can be a really critical point for a designer. And we've talked about this before, like concrete beams that are in like pure compression or tension axially can actually develop diagonal type forces that can be worse because they will tend to rip that concrete apart. And you can get stress fractures that occur like in diagonal directions, particularly in concrete. So designers typically need to know the maximum normal and the maximum shear stresses and also the planes that they act along. Now in chapter 13, you can start to look at some of this. They show you different methods of solving this. What we're kind of looking at is section 13.5, and that starts on 443. And so Tom goes through different methods of solving this at any plane, but we're not going to worry about all of those equations. What we're going to jump into is something called the Morse circle, which starts on section 13.7. So 13.7 is what we're going to pick up with here. Okay. So Morse circle is a technique, a graphical technique that was developed to solve this stuff, and it solves it really in a very, very slick method. Like I said, it's a real cool graphical technique, and it's used to determine maximum normal and shear stresses on elements that are stressed under that combined normal and shear stresses. So it's a way of looking at those very easily, and you can do it strictly graphical. So that's pretty cool. It was developed by Otto Mohr as a German engineer. He developed this in the 19th century, so late 1800s, and he set it all up by just simply using, like I said, you can use a scale and a compass and a couple straight edges, and you can do this completely graphic, but there's a few equations that you need, so it's not that big of a deal. But Morse circle plots normal stress along your x-axis and your y-axis, okay? And if you have it along, you may not have it along the y-axis, but if you're along the x-axis, we usually assign tension as positive and compression as negative, okay? And your stresses are always going to go along your y-axis, typically with a shear tending to rotate your element. So if it's clockwise, clockwise will be negative, counterclockwise will be positive. So your normal stresses, when it says it's along the x-axis, what that means is that's going to be your solutions along the x-axis, and your shear is going to be along the y-axis. That's going to be your maximum point. So here's a diagram, and I have this diagram out there for you. You can print this diagram out. It's a PDF file, so you might want to, because it's kind of hard to see what I've got going on here. But this is the development of Morse circle, and there's some critical points here. We're going to take a look at this. I'm going to run through a couple problems, so you'll see it's not that tough. Tom also has this diagram in his book. Let me see what page that's on for you. It is on page 453. So if you have your book, you might want to open that up. You can see that. Or like I said, I've got this diagram printed out for you as a PDF that you can open up and look at. But it's this is figure 1311, And I've got a little bit more on there than Tom does, so you can kind of take a look at this. So Moore's circle has some critical points. The first point is this point A and B. So these are related to your stresses. So you have a stress, kind of hard to read that, but that's a stress normal in the x direction, and that is what they call tau, which is your shear. So the two coordinates of that would be a normal stress and a shear stress. And this one is normal stress in the x direction and your shear stress along the x face in the y direction. And then B is the opposite of that. B is your normal stress in the y direction, and then your y value is your shear stress along the y plane in the x direction. Now, interestingly, C here is the center of the Moore's circle itself, and that always occurs on the x-axis. Okay, so C is always on the x-axis, so it's always going to have a value in the x direction, if you will, but the y of it will always be 0. Okay, if it's not, then you're doing something wrong. So you're going to basically, to set up Moore's circle, the first thing you'll do is you'll get this value here A, this value here B, and this value here C. And then you construct a line, and it should pass through 3 of those. The distance from C to A is the radius of Moore's circle, and I'll show you the calculation for that. And then, of course, C to B would also be the same, so that gives you the radius. Then you have critical points on Moore's circle. The point of maximum normal stress is over here at point A. So this is called maximum stress, and it's going to simply turn out to be the location of C's normal stress plus R. And then the minimum normal stress is going to be this side over here, which they define as Q. This will be your minimum normal stress, and it will be the coordinate of C's value minus R, and that'll get you that value. By the way, this circle can travel to the left or it could travel to the right. So the circle could be partially in the negative zone and partially in positive, or it could be all in negative or all in positive. So notice the way I've drawn it, it's all positive, but it doesn't always work out that way. And since the point of maximum shear stress is either at S or T, and they're the same, and they're just equal to the radius of this circle. So the radius of this circle going this way gives you S. That's a positive amount of shear stress, and the one going this way is your point of minimum shear. Okay, but they're going to be the same number. So whatever radius is, S and T are going to be equal. So then the other thing you can solve on this are the planes along which these points work. So to get the plane that the maximum or the minimum normal stress is, it's going to be related by this 2 theta here, which I'll show you. There's an equation to get that. So theta is actually going to be half of the number that we come up with here. And then the other one, we're going to come up this angle here, this 2 theta s. 2 theta s is going to be the plane along which the shear acts. Okay, so you're going to come up with basically a max and a min normal stress and the plane along which those act, and you're going to have a max and a min shear stress and the plane along which those would act. That's what Moore's circle is going to give you, and it does it in a really, really nice graphical way. So there's a couple of equations or a couple of things we need to look at. Okay, so the first thing, you're going to calculate or figure out the coordinates A, B, and C. Okay, so A is just the coordinates of the normal stress in the x direction and the shear stress along the x face in the y direction. And then B is the normal stress of the y direction, and the shear stress is going to be shear stress along the y face in the x direction. Okay, so shear average, that's your location of your center point of your circle. Notice it's always going to have C for its y coordinate. But what we do is we solve it by just taking the average. So you just take your average by calculating your normal x plus your normal y divided by 2. And that will give you what your value is here. So when we construct this, if we've done this properly, A, B, and C should all be on the same line. So this is linear, okay? Linear relationship. Radius is given by this very simple equation, which is, you can see it's just basically the Pythagorean theorem. So your normal stresses in the x and y direction subtracted minus 2 squared plus your shear stress along the x face in the y direction squared. And that'll give you your radius. So these are this is your setup of it. I'm going to go through this, so it's not that tough. It's actually pretty simple. And then to construct the actual angles, notice if you drop a perpendicular from that point A down to the axis itself, this value is actually tau, which is the shear stress along the x face in the y direction. And this distance here is given by the difference between the two stresses, stress in the normal minus the stress normal y, normal x divided by 2. So taking those guys, you can solve this angle by taking an arctangent relationship. So you'll notice that this divided by that arctangent, okay? So you can get the relationship there for your normal planes, and then you can get your 90 minus that. Now our actual answer, we're gonna have to divide by 2. So we'll see that at the end. So this is always gonna be double, okay? When you get your max and min values, points are, it's just gonna be your average stress plus the radius, average stress minus the radius. And your maximum shear points are going to be just plus or minus your radius. So it's a completely graphical way of doing this. It's really pretty cool as you work through it. So I'm going to step through this process. You can refer to Tom's figure 13.1, but you can use my diagram as well. So, but there's like 6 steps you kind of go through. And again, if you have a straight edge, and I usually use a scale, it's really nice, then everything works well. And then you can just use a compass and draw the circle. You don't even really need to draw the circle, but it's really instructive to be able to see that. And Thursday, we're going to go over some of these problems. So it might seem like they're really tough, but this isn't actually hard at all. Okay, so the first thing you're going to do is you're going to be given an element, and it's going to show you normal forces and it's going to show you shear forces. So you basically take those and develop the coordinates. So using the x face of the element, you're going to plot the x and the y coordinates of stress. Your normal stress is the x coordinate and your shear stress is the y coordinate. You're going to do that for point A. You're going to repeat that for point B. And that you're going to do then is draw a line that connects point A and B, and it will run right through your axis, and where it runs through the axis, that's actually your point C, the center of the circle. And that line represents the state of stress on the element. So you locate the center point C, and again, that point always runs through the axis X, so the y coordinate of that point is always 0. And the x coordinate of that point is the average stress, okay? The average normal stress. So you can kind of do these really quick. I'll show you once you get point A and B, that's your key. The rest of this just falls into place. Okay, so then to calculate the maximum and min stresses, they're going to be located at points R and Q respectively. And they're going to be they are a radius value away from the center of the circle. So you're going to add the radius to the center point's x value to get the max, and you're going to subtract the radius to get the min. Okay, so that's essentially what this is telling you. And then your maximum shear stresses are located at that S and T points, and those are going to be a radius away. So if I go back, let me go back to this diagram real quick. Okay, so what I'm saying here, so to get this is your maximum normal stress, R and Q minimum. So whatever the value of C is plus the radius, that's your max. This value minus the radius is your min. And the normal stresses of the shear stresses are just going to be straight up and down along the circle. And that's going to be the radius value here and the radius value there. Okay. And we'll see how this works. It's pretty simple. So the last thing you do then to locate those planes, Those are calculated from those angles. And the first angle is what they call that angle ACR. So take that's point A on the circle, C at the center, and R is another point on the circle. That gives you that theta angle, which is actually 2 theta. And then the other one is going to be the ACS angle, which is just 90 degrees minus that. Our answers, remember, are always going to be double the actual angle. So what we're going to have to do is divide those by 2 to get the total answer. Okay. So I know this probably seems pretty tough, but it actually is pretty simple. I'm going to run through an example with you. I'm going to do 2 examples, and we'll do more of these on Thursday, but you'll see if you're following along with me. I'll try to go pretty slow on this. Okay, so let me run over to my whiteboard now. I'm going to be kind of at a disadvantage because I'm not going to be able to solve this like I would normally like to, because I like to use a straight edge, or at least something that I can deal with. So I'm going to draw my little element. So very often when you have these types of problems, you're given, this is what you're going to be given. You're going to be given an element, and that element is going to have on it, let's see, it's going to have stresses that are shown on it. So in this case, we have a stress going this way and a stress going this way. And these stresses tend to be like this. So these are tensile stresses. And this is going to be 1,000 psi. So this is also 1,000 psi. Now keep in mind, this is your X and this is your Y in this picture. Okay, probably ought to remove that. Let me do that down a little bit differently. Let me put it down here. This is your X direction and this is your Y. Okay, just like we would normally think of it. So this thing also has shear stresses that are developed on it, and they usually kind of indicate them like this. Okay, so this has an X normal stress, but there is no stress in the Y direction. Okay, so you can have that. So there's no normal stress in the Y direction, but there is a stress in the X direction. Okay, these are my shear stresses, and this shear stress, this is the shear stress along the X face in the Y direction, and this is the shear stress in the along the Y face in the X direction. Okay, so they're always going to have the same value, but they're going to be opposite sign. So the first thing you do when you develop Moore's circle, here's what I do. It's just simply, if you get your coordinates first, then it all just comes together. So let me put those guys over here. So the first thing is I can calculate or determine sigma x. So this is the X normal stress, and since it's tension, we're going to say tension is positive. So we're going to call that 1,000. Okay. If you have a Y stress, which we don't, you'd have a value there, but our Y in the normal isn't anything, so it's just 0. Okay. So now the other thing we need to look at is the shear stresses, which they define as tau xy and tau yx. So this is the X. This is the X. This is refers to as the X face in the Y direction. This is along the Y face in the X direction. So the X face in the Y direction, it's 400. And we're going to say that clockwise is positive. I'm sorry, counterclockwise is positive, and clockwise is negative. So this one's tending to turn this element that way, so it's positive. This one is tending to turn it. It really, if you mess this up or you can reverse this, it doesn't matter. You'll get the exact same answers. It's just your circle's graphics will be different. That's all. Okay. So this is the biggest deal right here. Once you get these, the rest of Moore's circle falls into place. So for point A is going to be this guy, these are the coordinates of it, comma, positive 400. Oops. Okay, so this is your A value. Your B value is going to be 0, comma, negative 400. All right. Then we're also going to need to calculate the average stress because that's going to be the coordinate of the C point on the X. So average stress is defined as your sigma X plus your sigma Y divided by 2. Now, when you do these equations, you have to consider the sign. So if this guy's negative, then you're adding a negative and a positive together. In our case, we just have 1,000, and this one is 0 divided by 2. So that gives you a positive 500. And all of these stresses, they're all in PSI, so the whole unit is PSI, okay? So that allows us now to get the value of C, which is the center of the circle. And that's going to be the average stress, 500, and it's always 0. This will always be 0. So we have point A, point B, and point C. That's your major piece that you need to develop Morse circle. Is everybody okay so far?
Yeah.
It's a little confusing, I know. It's going to take you a little bit of doing this, okay? But the key thing is looking at this diagram, which is what you're going to be given, and getting these guys out of it, okay? Figuring that out. And the one that's always probably the most confusing is these shear stresses. But technically, like I said, it doesn't matter if you call them, if you reverse the negative and the positive, because it still works. That's the beauty.
Yeah, that's what I was wondering. What does that symbol mean next to the
This,
X? Yeah.
that means shear.
Okay.
It's just another way of, we've been calling shear sometimes V, right?
Yeah.
Tau is the same thing. Some people use that. Okay.
All right.
And unfortunately, that's what they're using now, because I think that was probably what Moore used originally when he developed it. Okay, so
All right.
so that just means shear. Okay, so this symbol is normal stress. This is shear stress, and that's what this isn't. If you got a force going this, or if you got a stress going this way, that's a normal stress. One going this way on the element is a normal stress, but when it's along the face like that, it's a shear stress. Okay. So that's probably the biggest deal right there. Okay. Now let me clean this up because I'm going to try to draw. Let me draw more circle here a minute. Okay, we're going to get into drawing it and show you. It's real simple. We've done most of the work right here. Let me tell you this. The cool thing about Morse circle, A, B, and C are they're all your work. Okay. If you blow these, you've blown the whole problem. But it's kind of hard to blow these because if these don't line up on a straight line, you got an issue. Okay. So that's why I'm saying if you take and actually plot these things, realistically, it really helps. Okay. So I'm gonna do something up here. Let me erase these real quick. Whoop, that's not what I wanted to do. Let me erase these and move this stuff because I'm gonna have to have room to show you what's going on here. And let me kill that. So I'm gonna put A up here. I'm gonna put A up here. And that's 1,400. B is 0, negative 400. And C, which is the center of the circle, is at 500, 0. Okay, so let me go ahead. I'm going to go ahead and delete these. Yeah, like I said, this will be a lot easier once we can do this on the board on Thursday. But it actually is not that tough. So I'm going to go ahead and construct an axis. Let me see if I can do this now. This is going to be hard for me. I'm going to put an axis right here. Actually, let me try something else. Okay, so I'm going to draw my axis right here. I'm going to put it over here. Now this is where if you have a straight edge, it really helps, and it really helps you think about what's going on here. So this direction, this is the direction of normal stress, okay? And this would be zero normal stress, so we're increasing positive normal stress. This would be negative normal stress. The y-axis is your shear stress, okay? And of course, this again is origin, so that would be positive shear stress, that would be negative shear stress. Okay, does everybody see that? So we're going to go in and plot these points, and this is where it's going to be hard for me. So I'm going to come over at 1,000 and up 400. So I'm just going to eyeball that point right there. That's going to be A. That's 1,400. B is going to be at 0 minus 400. So I'm trying to eyeball this. That would be 0, comma, minus 400. So if I connect a line between these guys from here to here, where that line crosses, this point right here is the center of the circle. This is going to be at 500, comma 0. So this is A, this is B, and this is C. Okay, you guys see that? So if you scale this properly, if you put a scale on here and this isn't 500, then something's wrong. Okay, so that's the cool thing about it, that if you've done this right, it's going to all work out graphically. Now, if I was able to do this, I don't know if I can try this. I don't think I'll be able to do it. Let me see something how this works. Oh, that might work. That's not too bad. My Morse circle, let me see something here. Let me undo that. That's not too bad. There's a circle right there. That's my Morse circle, okay? And you can notice this is going to be the point of maximum, oops. This is the point of maximum normal stress. This is going to be the point of minimum normal stress. And the points of maximum and minimum shear occur right through the circle's center. So you're going to have this line up and this line down. So this point right here is tau max, and this point is shear or tau min. Okay? So we have everything we need to solve it now. Let's see, we didn't solve the radius yet. Okay, so we need to solve the radius. So the radius is equal to your x value minus your y value divided by 2, and that is squared, plus your tau along the x face in the y direction squared, and then you take the square root of that. So you're really just using Pythagorean theorem, okay? So if I plug that stuff in, x was 1,000, y was 0, so that just goes to this. And tau x in the y direction was 400, so we're going to square that. So that will give us what this radius of this circle is. If you're calculating it, let me know what you get. I'll check my answer with you. I get 640.3. Anybody getting those numbers? Can I get that? 640.3?
Yeah.
Okay, so that would be the distance along the radius here. Okay. So to solve the max value, if you look back at that equation, you just take the average plus R. We determined that the average was 500. So that's going to be 500 plus 640. So that gives us 1,140.3 psi. Okay, so that's the positive. So this guy is in tension. The minimum value, you can see I'm running out of room, is your average minus R, 500 minus 640.3. Gives me a minus 140.3. This is in compression of PSI. You can notice that this is falling in the negative realm, so that makes sense. So the maximum amounts of shear are just equal to the radius. So you have, this is just going to be equal to plus or minus 640.3 psi. Maximum occurs here, minimum occurs here. They're always going to be the same, and they're always going to be equal to the radius. All right. Any questions on that?
No.
No, it's pretty sketchy. I know it's kind of hard, trust me, but we'll do another problem. So then the other thing we're going to do is calculate this guy here, which is called 2 theta. So in order to get that, we're going to take this side of that triangle, which just happens to be 400. And we just need to get this piece right here. Okay, so that is related by, if you take the x value minus the y value of your normal stress divided by 2, that'll get you this side right here. So 2 theta, and you can look at the equations for that, is the arctangent of your tau xy over your normal stress is subtracted divided by 2. So the average normal stress, in other words. So you get 400 divided by 1,000 minus 0 divided by 2. So when you take the arctangent of that, Let's see what we come up with. I should actually have an arc tangent in here. I'm running out of room, guys. So let's see what we come up with. So I got 38.66 degrees. So this would be the plane that the min and max normal stress is operating along. So that's what these guys are related to. And this plane would be rotated 38 degrees with respect to your x-axis. But remember, this angle is actually half of that. We need that to calculate the principal plane of the shear stress. So that's going to be equal to that minus 2 theta. So that is going to give us, when we subtract 90 minus the 38, we get 51.54. So these angles actually turn out to be theta and theta s. They're going to be half. So this angle is actually 19.3 degrees. And this one is actually 25.8 degrees. Okay, so we had this guy. There's an answer. That's your principal plane that your maximum and minimum normal stresses act along. And this is your principal plane that your maximum shear stresses act along. Okay. I know it seems like it's a big deal, but it's actually pretty simple. We're going to run through, let me run through another example with you. Okay. Give me a sec. I'll be right with you. Hey, I just got this thing on my phone. Okay. Are we completely lost, guys?
A little bit.
A little bit, yeah. Okay. I'm going to run through another example. Okay. Let me clean this up. Actually, let me do something real quick. I'm gonna, oops, I don't want to say that, change. It's a little bit hard for me to do on here just because I've got, so much I have to deal with. Oh, I keep doing the wrong thing here. Let's see, new. No, I don't want that. Okay, let me run back here real quick to the PowerPoints. Okay, so here's what we kind of did, all right? Now this picture is a little hard to see. I have that. You can open up my PDF on my website. It's a little bit better. But basically, you take that element and you determine, oh, hold on. That element, you're going to solve a point first, which is just the normal stress in the x direction and the shear stress along the x face in the y direction. So those are your x and y coordinates of point A. Point B is the normal stress in the y direction and the shear stress along the y face in the x direction. And then C is just really the average of those guys. So you calculate the C average, which is the normal stress average, and then its y coordinate's always 0. Once you construct A, B, and C, that's the key thing. The rest of it just works out from there. So then remember what we did was calculated a radius, which would be this distance, or that distance, or that distance, any of those. And the maximum point of normal stress occurs at this point R, and the minimum occurs at point Q. And then the maximum shear stress is always at S, and the minimum is always at T, and that's just related to the radius itself. And then the only other thing you have to deal with is this 2 theta angle and the 2 theta S. 2 theta is the angle of the plane along which your maximum normal stresses occur, and 2 theta S is the direction of the plane along which the normal or the shear stresses occur. Okay. So we used a couple of equations here. Again, these equations, really it's just solving that X, and for the point A, again, it's just your shear stress in the X along the and your shear stress and your normal, and then your shear stress Y and your normal, shear average. So you got this equation, and then you got that equation for radius. And then to get your other stuff, you've just solved those, okay? So let's try another example. We'll see if we can get this, and we're gonna look at this on Thursday, okay? So just if you go through the example in the book, and like I said, I think you'll be kind of okay. I just did the example in the book is where I got that from. I'm going to do another one that's a little bit different. So let's see if we can solve this. So let me run back over. This actually, I know it seems like it's probably a little difficult, but it's actually probably one of the easier things you'll do once you get the hang of it. So here's my little element that's given. And in this case, we have, let's see. We have 2 normal stresses, one here and one here. Okay. And then we have shear stress. We have a shear stress like this, and a shear stress like this. Okay, let me label these. So we have a shear stress here, or normal, excuse me. This is 5 kilopascals, and this is 5 kilopascals. And we have shear stresses here. This is 1 kilopascal. Okay, so as you look at this element, this is really the big deal right here. If you solve everything right here, everything else just comes into play. Notice we only have a shear or a normal stress in the y direction, so our x shear or x normal stress is going to be 0. This guy right here, we have a 1 kilopascal shear stress along the x face in the y direction, and it's going to be 1 kilopascal along the y face in the x direction. And this y is tending to turn this guy positive, and this guy's tending to turn it negative. So for the variables, there is no normal stress in the x because there's nothing happening this way, okay? But you do have a normal stress in the y, and since it's a tension, you're going to call that a plus 5 kilopascals. Did everybody see where I'm getting those from? Zero in the x, 5 in the y. We good on that?
So if there were arrows like pointing either to the right or to the left, then if they were like 5 kilopascals, then X would be 5.
Correct. Now, okay, let's look at this too, Max. If they were going away from the block, that would say their intention, so they would be positive, right?
Right.
If they were coming into the element, then that would be in compression, then they'd be negative.
Mm-hmm.
So yeah, you got it. It's that hard. Okay. So it's really pretty simple, right?
Mm-hmm.
Now this one's a little bit more confusing. Okay. So let's just look at this real quick. But you got the idea. So this is saying that I'm X and this is a YX. Okay. So what this is saying to you is this is the shear along the X face in the Y direction. So this is the shear along the X face, and the Y direction is clockwise. So we're going to call this +1 because we're just calling clockwise or counterclockwise. Excuse me, it's counterclockwise. Counterclockwise, we're saying is positive. This guy is the shear along the Y face in the X direction, and it's tending to be a clockwise. So this guy is going to be negative. Okay, because we're defining clockwise, negative, counterclockwise, positive. Again, you could reverse those and be totally correct. You'll get the same answers. Your diagonal line will just go one way as opposed to the other. So, okay. When I actually learned it, we did it reverse. Okay, so it's just not that big of a deal. Okay, so point A on your circle is this guy and this guy. So his coordinate would be 0, 1. Point B is this guy and this guy. So that's going to be 5, -1. Okay? So C is related to the average. So we need to calculate the average normal stress, which is that normal in the X plus normal in the Y divided by 2. Normal in the X is 0 plus 5 divided by 2 gives me a +2.5. Now you do have to consider signs, okay? So if this was a -5, you would have -5 divided by 2, so this would be a -2.5. All right? But remember, the points A, B, and C have to line up on the same line, so if they don't, when you plot them, you got an issue. So C, which is the center of the circle, is going to be the average 2.5, 0. And it'll always be 0, okay? Because it always has to lie on that x-axis, okay? These are the key 3 points when you do Morse circle. Get the A point, the B point, and the C point. Okay, is everybody okay with that? So the other thing I need to get, I don't need to do that right now, but I'm going to go ahead and do it. We can calculate R. R is easy to get. I'm going to tell you what, I'm going to put that here, but I'll probably erase it. So let's do the math here. R is related as normal X minus normal Y divided by 2. We're going to square that, plus the shear stress along the X face in the Y direction. Okay, so in here we have 0 minus 5 divided by 2. But since we square that, that'll be a positive number. And then this guy is 1. So 1 squared. Let's see what we come up with for radius. 5 divided by 2 is 2.5. 2.5 squared is 6.25 plus 1. 7.25. Square root of that gives me 2.69, and that would be your unit is actually going to be kilopascals. So, but that's our R value. So I'm going to put R up here because I need to have room to work. And let me go ahead and erase this. And then we can construct more circle. I'm going to move this guy over here too, okay? So that you guys know where that came from, but we're just going to have it as a value sitting up here. So we're going to have average, just in case we need that, that's 2.5. So these are the critical points, A, B, C, R is a critical value, and this average guy is a critical value. Okay, so I'm going to go in and we're going to try to draw more circle now. See if I can do this again. I did that pretty well last time, so that's my x-axis. That's going to be my y-axis. This is the normal stress. So all the normal stresses you just scale right off of here. And your shear stresses you scale in the y direction, okay? This is being my origin. So above that's going to be positive shear, below it's negative shear. Going this way is positive normal stress, going this way is negative normal stress, okay? So we're just going to plot point 1 first, then point B, and then we'll see that C should line up with that. And let me see if I can do this. I'm going to try to guesstimate. So I'm going to call that like 1 unit there. So this is going to be 0, 1. That would be point A. B is going to be 5 over. I'm going to guesstimate that. Boy, I hope I can get this. Let's see. That looks like about 5 and maybe 1 down. So I'm assuming it's like right there. This is where a straight edge is really helpful. Okay. So then when I connect those two guys from here to here, that's the diameter of Moore's circle. This point, if you scale it, what should the coordinates of this point be? Anybody tell me? That's point C. So what should the coordinates of that point be? 2.5, 0. If you lay a scale in there and that isn't 2.5, then something's wrong. Okay, so I mean you can't miss if you get A and B correct, C has to also work out. And if it doesn't, then you know you got an issue. Okay. There's like 90% of Moore's circle, and the rest of it's just constructing. Let me see if I can get this one to work now. Okay, there's my Moore's circle. So the point of maximum normal stress occurs there along the x-axis. The point of minimum normal stress is going to occur here. The point of maximum shear occurs along a line up to that point and down to that point. So we would have this guy is max and this guy is min. So we have maximum shear stress here, minimum shear stress here. Okay, so to solve R max, it's just the average plus R. So R max is equal to the average plus R. So that's going to be 2.5 plus 2.69 like 5.19. That would be kilopascals. And since it's plus, that's a tensile. That's a tensile stress. The minimum, and you can look at this diagram, you're just going to take that value and subtract that distance, which is R. So you just take simply the average minus R. So in this case, we have 2.5 minus 2.69. It's going to give us a negative 19 kilopascals. Notice the negative, just like my diagram shows, and you can literally, if you drew this properly, you could just literally scale that distance, and that would give you the same, should give you the same number theoretically. Okay. So then the maximum and minimum values of this, max is just going to be R plus, min is just simply minus R. That's also kilopascals. So that's just simply this distance up, that distance down, which is just R. So the other thing we need to do is calculate this angle. We're going to call that 2 theta. And then this angle, which relates to that, which is 2 theta s. And 2 theta is the angle that that plane of max and min normal stress occurs on, and then 2 theta s is the plane that the maximum shear stress occurs on. Okay. So to get 2 theta, it's the arctangent relationship of this guy, the x, the shear over the shear of x in the y direction, and then we're going to have 0 minus 5 divided by 2. When you take that relationship, you get 21.8. Now, the negative is just indicating that you're rotating it clockwise. That's all. So you can really drop the negative. And then 2 theta s is going to be 90 minus the 21.8, because we're just looking at absolute value. And that gives you 68.2. So again, we have to divide those by 2, and those are your answers. Okay. So again, the biggest thing with Moore's circle is looking at your given element, taking a look at getting those guys, getting your coordinate values for A, for B, and for C, solving your average, solving your radius, and everything else works the same way. Again, I would probably try to stress to you if you could use a straight edge and a compass. That really helps when you do this, and a scale. Okay. So, any questions anybody has over anything? Let's back up and see if there's any questions. I mean, first of all, I mean, does you guys kind of getting this? You got to do it a little bit just to understand it, but it's not tough.
So what you're looking for are the degrees, pretty much.
Well, you're looking for a couple things, okay? What you're looking for is the maximum value of normal stress, the
Okay.
minimum value of normal stress, the maximum and minimum of the shear stress, okay? And then this angle is the angle along which this guy occurs, okay? And this angle, and remember you have to divide this by 2, right? Because these angles are double what they should be. This angle then is the angle along which this occurs. So you're really looking for 4 things, okay?
Okay.
You're looking for min and max, well that would be, you could consider that 1 and that 2, and then there's your 2 angles, all right?
All right.
what's kind of cool, you could go in, what's cool about this graphical solution is literally, if you wanted to know, like, say, what the stress was right there, you could just scale that distance. You could scale it right off of there. So if you laid a scale from here to here, that's your value of normal stress, and this would be your value of shear stress. So it's kind of a really cool thing the way it was developed. But yeah, that's a good point, Max. What you're after is min and max normal stress, min and max shear stress, and the angles of the planes along which those guys occur. And that's what we're looking at, okay? And what we're doing is just combining those two together. Does that make sense now?
Yeah.
Okay. The process and the procedure is really pretty simple. It's once you get the hang of what's going on here. This element, looking at this element, is kind of the hardest thing, and it's always, people always get really tripped up in the shear, okay? But these are usually pretty simple. I mean, if they're going in the y direction, you have a y value, you got something. X, in this case, we have nothing, like we said before. So usually you don't have problems with the normal stresses. Shear stresses are the ones that usually give people fits. But if you're not sure, it doesn't really matter. Like I said, if I called that negative and that positive, all that's going to do is skew this line this way, but the angles will still come out. Radius will still, everything still comes out right. So that's kind of the neat thing too, because it doesn't matter whether you call clockwise positive or clockwise negative. Okay, but the book does, Tom does use counterclockwise as positive and clockwise as negative. Okay, so like I said, the book I used at college, we did it reverse, but it's no different. All right. Anybody questions about anything? Deck project stuff, okay.
It's coming along.
Okay. I would like to get those on Thursday, but you know, I do understand we're somewhat limited. Your access to me. I mean, you do have access if you want to contact me. I'm more than happy to work with you. But I would say bring in what you got Thursday. I'm gonna take a look at it, and if I look through it and I can say, look, you need to do this, you need to do that, we could just finish it up for the following Thursday. How's that sound?
That works.
And if you think you're done, then certainly I would take it. Okay. So what I want to do on Thursday is I want to go over I want to finish all the problems out of chapter 13. And I don't think I've assigned you any problems for Morse circle. So let me go ahead and do that right now. And I'll post those numbers up on Blackboard. But and then any other question out of 13, oh, actually 11, 12, and 13, that's what we're going to focus on, okay? So I want you to look over everything at this point. You should be able to do problems 21 through 25, okay? Problems 21 through 25. Those are more circle problems. Now, let me just tell you, they're going to ask you to calculate angles at 30 degrees, 20 degrees, and 10 degrees. Don't worry about that, okay? Just solve the maximum conditions that I just showed you. So don't worry about the 10 degrees, 20 degrees, and 30 degrees. That's meaningless for what we're looking at, okay? Just do the Morse circle piece.
You said which ones?
21 through 25. I'll go ahead and post that up on Blackboard too, because I don't think it has it on there, and I'm not sure that it's on your syllabus, because I wasn't sure that we were going to even get to Morse circle, but we did. So we'll take a look at those. So I'll take a look at some of those problems with you on Thursday. Any other problems that we've assigned and looked at out of chapter 13, definitely we should look at. I mean, there's a lot in there. Those eccentric problems, problem 6, 7, 8, 9, those are all eccentric loads. 10, yeah, there's a bunch in there, okay? So make sure that you look at 13. I would actually like you to spend more time on the earlier parts of chapter 13 than Morse circle, but I don't want you to not spend any time. So I want to cover completely everything out of 13. And then we can revisit 12 and 11 if we need to. Okay, how's that sound?
Yep.
Okay. Anybody else questions? Sounds like somebody's trying to talk to me, but I can't. I'm going to go ahead and stop the recording.